Hi guys, here's video 3-4. See your checklist for when to watch it. And before we jump into it, I want to just do a few examples with you that I'd like you not to write down. So don't write these down. All right, so this first one we're going to take, so d dx just means that you're taking the derivative. Okay, so let me just say right here that this is the same as if I went 4r to the third prime or something like that. Okay, so these mean the same exact thing. But when you do d dx, it's clear to your reader, like if you just see like a bracket and then a prime on the outside, you don't know, like maybe r is the independent variable. So the independent variable is usually x, like f of x. So the independent variable is the input, like the most innermost input. So I don't know that r is the independent variable. It's sort of implied if I'm using this notation, but down here, if I see d dx and then 4r to the third, I know that r is not the independent variable. X is the independent variable. So that's what this is telling me. It's saying take the derivative with respect to x of that. And so r is not like the innermost input. X is, but I don't see it like in the in the expression. So anyway, anytime you do implicit differentiation, you've got to do chain rule. So the innermost function, I'll say, is r, and then it's 4 blank to the third. So the derivative of r with respect to x is dr dx, and the derivative of this is 12 blank to the second, and then r goes back inside. And generally we write the dr dx at the end. So you go 12 r squared dr dx. Okay, so that's how you do implicit differentiation. You're basically just doing chain rule on everything. But instead of having like, but the inside derivative looks like this. All right, let's do this one. So this time we're doing the derivative with respect to x of sine of x. So since it's d dx, we know that x is the independent variable. But since I'm doing implicit differentiation, I'll just do chain rule on everything. Innermost function is x. The outer function is sine of blank. So this is dx over dx. All right, last time it was dr dx. This time it's dx dx. And then derivative of sine is cosine of blank, and x goes back inside. So this is cosine of x times dx dx. But then this is just 1. If you're taking the derivative of x with respect to x, that's just a 1. And actually the way that the notation works, it helps you understand that it's 1 because it's like dx over dx. So you could think of those as canceling. And then this is just cosine of x. So that's just the normal. You just end up with a normal derivative. So if you're taking the derivative with respect to a variable, and it's that variable that's the input in the function, then you just end up with like the normal derivative at the end. Okay, anyway, let's do this one. I'm going to go faster. I'm not going to use the in and out chart. So I'm taking the derivative with respect to x of this. I know that the derivative of natural log is 1 over whatever, so it's going to be 1 over z, and then I go times dz dx. So you just do the normal derivative, and then you multiply it by the derivative of the input variable. Okay, now this one here, so same, I'll do just the normal derivative, which is 14x to the 6th times the derivative of the input variable in Leibniz notation, but dx dx, that's just a 1. So you end up with 14x to the 6th. So that ends up just being like the normal derivative. Okay, now we're jumping into these problems. So implicit differentiation is really just chain rule. It's another version of chain rule. But you don't even have to show really the in and out chart, because the inside function is usually something that we don't have a whole lot of information about, or we don't have it expressed explicitly. That's why it's called implicit differentiation. We haven't expressed the innermost function explicitly as a function of something else. But anyway, in each expression below, y is a function of x. Differentiate each expression with respect to x. So differentiate means take the derivative. So I need the derivative with respect to x of 9y. So you look at the function you're taking the derivative of. So I take the normal derivative, which would be 9, and then I multiply it by the derivative of the input, which is y. So there it is. This one, the derivative with respect to x of 6y to the third is 18y squared times the derivative of the input, which is y. All right, now this one I need d dx tangent of 7y squared. Okay, we've actually got to do a, all right, so if I was just gonna do the normal derivative of this thing here, I would need chain rule. So inside, outside. Inside we've got 7y squared, outside is tangent of blank. So the derivative is going to be 14y times secant squared of blank, that's the derivative of that one, and then I plug this back in, 7y squared, but then we're doing implicit differentiation, which is basically just chain rule on everything, so you're always going to have d whatever dx at the end. Okay, now find y prime by implicit differentiation. So up here, let's write this because this is important. When you're doing these problems, it's important that you know that y prime is the same as dy dx, because what we're going to do in these problems is that we're going to start off using Leibniz notation, which is dy dx, and then we're going to switch at the end to prime notation, because prime notation makes it easier to do the algebra. So makes it easier to do the solving. So we're going to find y prime. So what you do, guys, is you go like this. Okay, so in the future, in the past, I would have you go like at the very beginning, take, you know, the derivative like this, okay, of like every term involved. But instead of that, so let's say we passed. In the past, we would do that. Now we're gonna, and you could still do this in certain situations, but if you're doing implicit differentiation, you want to go like this. So you want to go, instead of the bracket, you go like this, d dx x squared. So that means we're going to take the derivative of x squared with respect to x, so as though x were the independent variable, plus d dx y squared 49. Okay, so you take the derivative of x squared, which is 2x, and then you multiply by dx dx. So whatever the variable is, and then over dx, plus 2y times dy dx equals, the derivative of a constant is just 0, and I would normally go d whatever the variable is over dx, but there's no variable even to work with here, so it's nothing, it's just 0. Okay, now the next observation to make is that dx over dx, that's just 1. All right, so we actually have 2x plus 2y dy dx equals 0. And now up here, I'm going to switch to prime. So switch to y prime. So dy dx is y prime. So 2x plus 2y, y prime equals 0. And I just switched to y prime because it's just easier to do the algebra with y prime instead of dy dx. So I'm going to subtract 2x from both sides. And I've got this. I'm going to divide both sides by 2y. And I've got that. And then I end up with y prime equals negative x over y. Okay, let's do another example. So find y prime by implicit differentiation. So implicit differentiation means I'm going to go d dx on every term. So I've got one term, two terms on the left side of the equation, and then a third term on the right side. So I go like this. You might want to write small here. I ran out of room when I tried to make this video last night. Y cosine of x. Okay, so just like this. You will notice here we're taking the derivative of a product. That's a product. So we're going to need product rule. And then again, here we're taking the derivative of a product of two functions. So we will need product rule. And I'm just going to color code a little bit here so you can see where the stuff is going. So I'll show you where that goes. So for this, I need the derivative with respect to x of x. And then I just need to bring down the cosine of y. And often I put parentheses around that, but they often leave it off. And then it's going to be plus, I just bring down the x, and then I multiply by the derivative with respect to x of cosine of y. Okay, so that thing that I underlined in pink becomes that when I expand it out with product rule. I still haven't really taken the derivatives yet, but this is like when we go bracket prime, bracket plus, bracket, bracket prime. That's basically what this is right here. And then this plus sign I bring down there. And then I'm going to set up product rule for that. So it's d dx of y, bring down the cosine of x, plus bring down the y, d dx cosine of x, equals, and then I'll just do this right away. The derivative of a constant is just 1. And I don't need a d anything over dx because there's no variable. Only when there's a variable you do d dx at the end. Okay, so that's where those things went. All right, so on the pink I used product rule, on the green I used product rule, and it became those. And now I'm going to go through and actually do the derivatives. So so the derivative of x with respect to x, that's just dx over dx. Bring down the cosine of y plus x. Now, the derivative here, derivative of cosine is negative sine of y. But then implicit differentiation, you're essentially doing chain rule, so you've always got to multiply by the derivative of the inside. So the innermost function here was x. Well, so it was like 1. Yeah, so the derivative of x is 1, and then I multiplied it by dx. So the derivative of cosine of y is negative sine of y, but then I multiply it by dy dx. Plus, the derivative of y is 1 times dy dx. Just bring down the cosine of x. Plus, just bringing down the y. Derivative of cosine is negative sine of x. And then derivative of the inside is dx dx. Ooh, that was a 0 before. I think I said 0. Okay, now I'm going to find the dx dx's and just cancel those out because those are 1. All right, so dx dx, that's just a 1. Anywhere else, right here, that's just a 1. And in the same step, I'll replace the dy dx's with y prime. Okay, so those are actually y primes, and then I'm going to have to solve for y prime. So this is cosine of y minus x sine of y, y prime. This just became y prime. I'm just switching notation here. And if anything I do doesn't make sense, it's time to pause the video and try to figure it out. You want to understand everything that I do. And if you can't, you want to ask me. So plus cosine of x, or ask someone else, times y prime. I just changed that to y prime. Minus sine of x, y equals 0. Okay, now I've got to get the y prime terms by themselves so that I can factor out a y. This is called separating the variables. So I got to separate the y prime terms from the other terms. So there's the y prime terms. So I've got to get these terms on the right side of the equation, the underlined pink ones, and then I want to leave these blue ones over here. So I'm going to subtract cosine y from both sides, and I'm going to add sine x. Sine x times y to both sides. Okay, this could have been y sine of x, which I kind of wish I wrote it like that. All right, so I'm going to end up with negative x sine of y, y prime, plus cosine of x, y prime, equals, I'm getting the pink ones on the other side, so I'll add this one to both sides, and I'll put the y in front, and then minus cosine of y. And the whole reason that you separate the variables is because now y prime and y prime, so y prime is a common factor, so I can just factor it out, and you end up with this equals y sine of x minus cosine of y. And now that you've factored this out, you can divide both sides by this parentheses here. So you end up with y prime equaling y sine of x minus cosine of y all over negative x sine of y. Okay, so basically implicit differentiation is when you just do chain rule on everything with Leibniz notation. All right, and it ended up getting us that this was y prime. And you have x's and y's mixed up. You have x's and y's mixed up. That's how you know you've got to use implicit differentiation. And then you just do chain rule on everything you take the derivative of. All right, guys, I'll talk to you soon. Bye-bye.